Okay, so let us talk about this new and the last topic of this chapter under the title of complex numbers. So they call it imaginary numbers, but let us see what is going on. If I want to give you a gentle motivation, what's going on? The reason that we actually wanted to have some numbers with, I would say, strange properties is because of solving equations. If you want to solve polynomial equations, for example, the smallest set of mathematics that was enough for us before was the set of natural numbers. For example, you have it from 1, 2, 3, 4, etc. And then assume that you have a polynomial equation. What do I mean by a polynomial equation? I mean that you have a polynomial equal to 0. For example, you have a first degree equation equal to 0, second degree equation equal to 0, etc., etc. So, for example, this is enough. If I want to solve some of these polynomial equations, what do I mean by that? I mean, for example, if I ask you to solve this equation, if you solve, the answer is already in this set. Yeah? So if I solve this equation, you get, I want to make the examples as simple as possible because I just want to see, I want you to understand what is going on. Okay, so then x becomes equal to 1. So it means that for this equation, this set is actually enough. What do I mean by that? I mean that when you find the answer is a number there. Okay? But it is not enough for solving all possible equations. For example, if I go and solve this problem, 2x plus 4 equals to 0, then of course you know the answer. I move 4 to the right, it becomes negative 4. Then I divide by 2, it becomes x equals to negative 2. So it means that if you do not include negative numbers in your set, then you will not be able to solve this equation. If you just restrict yourself only to these numbers, you would say that there are no solutions for this equation because the only solution to this equation is a negative number and this is not there. So this is why you extend this set to a bigger set, and that set is called the set of integers. You say that, okay, let us append negative numbers and 0 to this. So you would append, for example, minus 4, minus 3, minus 2, minus 1, 0, and 1, 2, 3, 4, etc. as before. Now this set is completely enough for solving both of them. The answers are both in this set. But again, there are some other polynomials equations that the solution is not in this set. And then probably the simplest possible scenario that I can make it for you is this equation. This is again another equation. If I ask you to solve this equation, what you do, you move 1 to the right, and then you divide by 2, so x becomes 1 over 2, or 0.5. But again, this was enough for solving these two equations, but still it is not enough for solving this equation. It means that I get a root which is not inside this set. So I extend this set to a bigger set by appending all fractional numbers to this set. And that would be the set of rational numbers, yes? So I extend this set to a new set, which I call it the set of rational numbers. And then it's better to define them. They are defined to be all possible fractions so that the numerator and the denominator are coming from the set of integers, but of course, b shouldn't be equal to 0. Yes? So then, this set is actually enough for solving this equation. So this is the biggest set that we have so far. It is completely enough to solve this equation, and this equation. By being enough, I mean that when you find the answers are members of this set. Yes? Why this is a member of that set, even though it is not in a fraction form? Because every number can be written in a fraction form with the denominator equal to 1. So these are all members of the set of rational numbers. But the problem, again, this seems to be not enough for some equations. Yes, for example, which equation can you imagine? Very simple. I just want to give you. I want you to give me simple examples. Yes.
X squared is equal to -1.
No, it is a little bit ahead of the time. Okay, we will come to this later. But before that step, still it is not enough. So I mean, you see, up to here is good, but then there is a reason that we go to the real numbers. That equation that you mentioned is the reason we go to complex numbers. But why we need to go to real numbers? Because, by the way, do you think every number, forget about complex numbers for the time being, do you think that every number that you can imagine is in this set? Can you give me a counter example? Can you imagine a number which is not here, but it still is real number? Yes?
Pi.
Pi. Pi is a number which is not there. Yes? Or more famous one, square root of 2. Square root of 2 is all not there. Because people realize that pi is not there later. But the famous number that came out that it is not there is the square root of 2, and that is after Pythagoras was able to show the theorem. So people didn't believe that there are some irrational numbers before. But Pythagoras actually came up with this theorem, and now it is easy to imagine that, okay, I have a right angle triangle whose this length is 1 meter or whatever, 1 meter, and then this is also 1 meter. And then Pythagoras already showed that if this is c, then c squared is equal to 1 squared plus 1 squared, and then it becomes 2. So then it means that they were looking for a number whose second power is 2. They thought that this number should be there, but the proof came later that no, you cannot find any number. It's not possible to find a number here so that when you square it, it becomes 2. Yes, because on the one hand, people using this geometric picture, they understand that this number should exist somewhere. Yes, this is the existence of this number is clear by this picture. I draw this picture, 1 meters here, 1 meters there. I draw it in a way that they are perpendicular to each other and just connect these 2 points. According to Pythagoras' theorem, which was already proven, it means that this length should be a number so that when I square it, it becomes 2. So the existence of such a number is in front of our eyes. Yes, we have that line segment whose length is such that when I square that length, it becomes 2. So on the one hand, the existence of such a number is clear from this geometric picture. But before that, at that time, people only knew about this set. People doesn't know about any other sets. Okay, so it means that there are some, and then it was not clear. So they was thinking that, okay, there is a number here, even though I cannot point to which number, but might be there is a number whose square is equal to 2. So they might think that, okay, c is still there. But the proof of this comes later. You also see it in Math 4, why there are no numbers there, so that when you square it, it becomes 2. Okay, so why there is no fractions, so that when you square it, it becomes equal to 2. It is not very trivial. So then it means that there is something going on. It means that if someone asks me to solve this equation, this is still a polynomial equation, because the left-hand side is a polynomial, and I put it equal to 0. If I want to solve it, x squared becomes 2. So then this number became famous later. That number is the square root of 2. It becomes plus or minus, of course, but this does not belong to the set of real numbers. To the set of rational numbers. So it means that if I stop there, many of the equations can be solved in that set, but still there are some polynomials that cannot be solved. So it means that we also start appending these type of numbers called irrational numbers to this set, and then make the set bigger. Okay, and that set is called the set of real numbers. So the set of the real numbers actually is the set of rational numbers. Appending it, this means union, or appending, I would say, the set of irrational numbers to it. So people was thinking that, okay, might be this set is enough for all polynomial equations. If I append all these type of numbers like pi, like Euler number e, like square root of 2, square root of 3, if we add all these numbers to the previous set, might be that is completely enough to solve all polynomial equations. But as Cameron pointed out, it turns out that no, this is not still enough. Yes? Why? So let's see what is happening. We had a set, let me call it n. We make it a little bit bigger. We called it the set of integers. So it means that whatever is in n is already in z, but z contains more new elements. And then it was not enough, so we extended it to the set of rational numbers. And then it means that the set of rational numbers already contains everything in z, because whatever is in z can be written as a fraction. Yes, for example, -4 can be written as -4/1, and that is a fraction of this type. So whatever is in z is automatically in q, but there are some elements in q that are not already in z. For example, 1/2. 1/2 is in q, but it is not in z. So it means that there are some new elements. And then it turned out that this is not enough for some problems like this. So we had to append some new numbers to this system. So we extend it again and make it equal to the set of real numbers. So this is the most of the time we use this hierarchy as the set of numbers. Okay? But then this turns out that this is not, again, enough for some of the equations. And what is that? As Cameron pointed out, if you want to solve this equation, x squared, the equations, by the way, are very simple and in front of your eyes. If you want to solve this equation, you will not be able to find a solution for this equation there. Why is that? You don't need to be very smart to understand that, yes? Exactly, because when I square this one, we talked about this. What is the minimum value of this? X squared is non-negative. And then I add to it, it becomes greater than or equal to 1. So how could I expect that this one becomes equal to 0? So for this simple reason, we realize that there is no numbers there that can solve this equation. And now the king of mathematics, called Friedrich Gauss, actually was thinking about this problem. And he was thinking that, okay, let us construct the set of real numbers. So let us extend the set of real numbers to a set that he wanted to actually discover or invent, so that it will contain this solution of this equation as well. And that is exactly more or less the same. I want you to have the same feeling. When people didn't know about the square root 2, the square root of 2 was an imaginary number for them. Because I want to have the same feeling, yes? People didn't know about this number, square root of 2. They didn't know about that. They thought that every number can be written as a fraction at the end, yes? But then suddenly they realized there should be a number. First of all, on the one hand, they realized that because of this theorem, there should be a number whose square is equal to 2, because I was able to construct it in front of my eyes. On the other hand, people was able to show mathematically that no, don't look inside here. Even though there are infinitely many possibilities, by mathematical argument, they were able to show that don't look there. You cannot find a number there with that property. So you can immediately have the same feeling. People started talking about the number that is here. I call it a square root of 2. And I use a symbol for it, yes? Which symbol you use for this number? You say this one. But by the way, if I ask you what is this one, what is your answer? What is the square root of 2? The square root of 2 is a number whose power of 2 is 2. That's it. This is, I just want you to understand, because when I go to imaginary numbers, suddenly you start resisting. But I want you to feel the same idea, yes? Square root of 2 was not clear for people, but they realized there should be some number. And then let us call, what is, so then they say that, okay, there is a number, so it deserves a name. We call it the square root of 2, and it deserves a symbol. So we show this with this symbol, yes, square root of 2. But if someone asks you what is a square root of 2, you would say a square root of 2 is a number, so that when I square it, it becomes 2. That's it. Okay? And that is the same idea. But then it turns out that this is not enough for our purposes here. So he was thinking that, okay, let me define a number whose square root is -1. Sorry, whose square is -1. That is imagining. Again, the same scenario. This number, of course, definitely is not here. But for simpler reason. It was much harder for this argument is much harder for these people at that time to say that there is no number here whose square is equal to 2. It was harder. You will see the proof of this in Math 4. But it is not hard for you to immediately realize, no, there is no number here. So with this property, that simple argument works. But now let us imagine that I extend this to something imaginary, and then we call it the set of complex numbers, so that it also contains a number whose power of 2 is -1. And there is that number is denoted by I. Okay, imaginary number, and that's called imaginary unit. So you see, this is the definition of I. I want to have the same feeling with the square root of 2, inventing a new symbol, the same feeling with introducing a symbol I. Okay? So Gauss said that, okay, let us add a rule on top of the rules that we already know for numbers. Let us imagine that there is a number with this property, and let us explore the consequences. Yes?
Is that a 2 or is that?
No, this is I. This is 2. This is 2. I to power 2. I will write them explicitly. Don't worry about them. Yeah. So you can imagine it in this way. You can imagine that I am adding a new creature, and I call it the imaginary unit. If you tell me what is the imaginary unit, what I can say is that that's a number. Definitely this number is not a real number. But let me imagine that there is a number beyond the set of real numbers with that property. So this is why people call it imaginary. Okay? And then let us explore the consequences of this simple assumption. It's like a game for the time being. It might be a useless game. So what's the problem? I just bring something in, that's a fun thing, I just explore its consequences. That's one possibility. But it turns out that it is nearly 300 years that it is exploring and flourishing. So it means this idea is not useless, because then, I don't know, by thinking about this, imagining something like that, you can solve a lot of problems in the real life, in the real system, that you couldn't solve if the Gauss wasn't thinking in this way. Okay, is that clear somehow? So this is the way. So the way that he was doing, he was actually exploring this. Let us find a set that has this solution. And in his PhD thesis, he actually was able to show that, don't worry, you don't need to make it bigger anymore. This is completely enough. If you want to solve all polynomial equations, you will not face this problem anymore, okay? Forever, even though you cannot see all polynomial equations. So actually, Gauss was able to show that if you, from now on until the end of the world, start writing polynomials equations and put them equal to 0, this set is completely enough to solve this polynomial equation, meaning that the roots are here, not beyond that. So he was able to show that you don't need to extend the set of complex numbers to a bigger number if your civilization is going to be more advanced. It doesn't depend on that. If your goal is to solve polynomial equations, that is the final story. You don't need to extend over that. Yes?
Okay, so you say for polynomial equations, but is there like another set for like other types of equations?
No, then it turns out that that is completely enough for all possible solutions of all equations.
So imaginary numbers, that's the final for
Yeah.
everything.
Yeah.
Okay.
Yeah, that's good. Yeah, so what I'm saying is that I want you to have this feeling. But now, this is not the job of mathematician to think about the consequences in the universe. Yes? So it was just a mathematical curiosity, but it turns out it was a very helpful, useful question, because people were struggling how to factorize polynomials and things like that. This theorem and this way of thinking was very helpful to solve problems within the mathematics itself. Is that clear? It was nearly around 18th century. Okay? Before that, Newton actually discovered his formulas. Yes. So, for example, this is the second law of Newton. So, in principle, if I shoot a ball, and if you give me the forces acting on the ball, and if you give me the initial position and initial velocity of the ball, using this formula, I can predict at which time the ball is where. Okay, so that is the power of physics, actually, using mathematical rules. But I just want to tell you, so that was actually these numbers that you see here are real numbers. Force, the magnitude of a force is a number, 5 newtons, I don't know, 10 newtons. And mass is something for the ball, you measure it, and the acceleration is a number. But then assume that people was thinking electron is also something like a ball, okay? That's a point particle, okay? And then we wanted to do the same thing for electron. Of course, this becomes a little bit complicated, but you can just imagine it in this way. Assume that I shoot an electron with some force, I hit it or something, and then I have the mass of the electron. Assume that I know the force is acting on the electron. So I want to solve this equation for the electron and to see where this electron lies, for example, 2 seconds later. And it turns out that when we predict, we calculate on the paper, and when we go and experiment it, they are not exactly the same. There are a very big discrepancy between the experiment and the theoretical part. It was not the case for the ball, a big ball, just cannonball or whatever. Yes? And you just use it and predict, okay? And this is actually happening in the artillery. I don't know the word. What was that? Artillery?
Artillery.
Artillery. Yes, what?
Artillery.
Artillery, yes. In the war between them. So the way that you measure the angle of that cannon pipe or whatever is actually use this formula, so then you can hit the enemy. Exactly. This is why this formula is working. But if you want to do the same thing using electron, it doesn't work. Okay? And then in the beginning of the 20th century, people realized that, okay, if we want to predict the behavior of an electron, we need to have a more complicated equation. And the equation, you don't need to be bothered about the form of the equation. It's something like this. It's a little bit complicated, and that's called Newton's law. That's the Schrödinger equation.
Schrödinger.
So Schrödinger is like this. Austrian Dinger, yes. Erwin Schrödinger, yes. So that was the equation. Let me write the equation. Something like this. If I remember correctly. So the force part is actually in this term. This is the force part somehow. And this is the mass of the electron. And that is something called the wave function. It's a little bit complicated, but don't worry about that. So you see that this equation is replaced by equation like this. If I just use this equation to predict the behavior of the electron, it fails again. Yes?
Is that a 24 or something?
No, this symbol is psi. It's a Greek letter.
Psi, like the
psychology, something.
Okay,
like
not like the Korean guy.
Yeah,
No.
style.
Yeah, that's the same psi.
Okay.
Yeah, because that's also the same shape. Yeah. And then this is derivative somehow, but a little bit more advanced derivative. It's called partial derivative, and this 2 means that the second derivative. But don't get confused. But this is the mass. Okay? And then if you predict the behavior of the electron using this formula, then it turns out to be wrong again. But interestingly, if you put this I, where Gauss actually invented I don't know, 200 years back, more or less. When you put this I here and then use this new equation to predict the behavior of the electron, it turns out to be everything right. Okay, so then, I don't know, still you want to call it imaginary or not, that's up to you, yes? Because electron probably is very real in our universe. And then without this I, the behavior of this real thing doesn't work. But if I put this I here, then it works. Okay. But still, there is a big difference between real numbers and complex numbers. Even though when I put this I, it turns out that I will work. Everything works fine. Apparently, up to this point, might be in the future experiments. There are some violations to this. We don't know. But the point is that whenever you measure a thing, so there is a big distinction between complex numbers still with real numbers. Whenever you measure something, you cannot measure a complex number. When I weigh, for example, when I measure the mass of the electron, I will not get a complex number like I definitely get a real number. So in this sense, in the sense of measurement, all the numbers that you get out from measurements are real numbers. Okay, so you cannot say that, okay, the electric charge of electron is 2I or whatever. 2I, I mean this I. No, the charge of electron is actually a real number. So in that sense, still, there is a unique position for the set of real numbers because the values of measurements are real, yes? But anyway, if you don't put this I, this guy didn't know anything about this field of physics, which is called quantum mechanics, yes? But it seems that this question, which was completely developed for some mathematical purpose, it's very useful even in physics, okay? And this is very, very nice collaboration between physics and mathematics, and this has happened a lot of times. Okay, so this is an introduction actually to what I wanted to talk about. But at the level of your lesson, you need to learn a little bit about the algebra. And the algebra is more or less the same, everything that you do with polynomials, but this time you do with polynomials type expressions which involve I. But then there is a rule on top of that. If I squared appears in your calculation, take it away and put -1 instead. So that is the rule of the game. Yes? So now let us do it formally, okay? Any questions?
No.
Okay, so let us do now formally. So let me write definition. Now that we understand more or less what's going on, we need to define it formally. So a complex number is a number of the form you have A and you have plus B multiplied by I. Any number of this combination, A plus BI, where A and B are real numbers, and I called the imaginary unit, has the property that is defined by, let me write it in this way, is defined by I squared equals to -1 is called a complex number. Okay, so it is not exact. So you see, when I wanted to talk about rational numbers, I was not independent from understanding the set of integers, because I told you that a rational number is a fraction whose numerator and denominator is an integer. So the set of integer helped me to define the set of rational numbers for you. More or less the same analogy is here. The set of real numbers is helping me to define for you a complex number. I'm saying that a complex number is a combination of this form where A and B are real numbers, but then something new is here, and that is I. If someone asks you what is I, the name of I is first of all the imaginary unit, and then it is a symbol. It is a number in the world of complex numbers whose square is equal to -1. That's called a complex number. Yes? And then A in A plus B in the complex number A plus BI, A is called the real part. This is a little bit confusing. A is called the real part. These are terminologies, okay, so these are conventions. Is called the real part, even though both of them are real. I will explain them. A is called the real part, and B is called the imaginary part. So let me give you an example, then I will come to you. Okay, do you have a question? Yes, I will come to your question. So let me just give you an example.
Does it say B is the imaginary part?
Yes,
Or BI?
and B is called the imaginary part.
Okay.
A is called the real part, and B is called the imaginary part. It might be a little bit confusing because here I'm saying that A and B are both real, and now I'm saying that A is called the imaginary part, real part, and B is called the imaginary part. These are the words that mathematicians use for this. You need to learn that. So what I'm saying is that, for example, 2 plus 3 multiplied by I is a complex number. That's a complex number. Okay? And the one without I is called the real part. And the number, so you see this expression is the real part. This number, even though itself is real, this is called the imaginary part. So don't get confused. The imaginary part is a real number, but I'm just calling it different. Okay? So, for example, I can give you more examples. For example, I can have 3 plus minus 2i. Okay? So this is also a complex number. What is the real part? The real part is positive 3. The imaginary part is -2, because you can imagine it in this way. All the rules of the game that you have for real numbers are also there for imaginary numbers. So there is another name for writing this. You can write plus -2 times I. So there is no difference between this and that based on the rules that we already learned in normal real number system. I am telling you that Gauss actually added only one rule on top of all the rules we had. Okay? So we have all the rules, but we add something to that, and that is I squared is equal to -1. Yes, please?
Why do you say that the imaginary part is -2? Why not -2i?
No, that is the definition. That's a little bit unfortunate. You can say that this part is imaginary part. You are right, but this number is called the imaginary part. Okay, the number next to I is the imaginary part by the definition. You could define it in a different way, but this is the way that they have defined it. Okay, by the way, do you think that 5 itself is also an imaginary number?
No.
If it is not, then we are in trouble.
Okay.
Because we are supposed to extend. Yes, we had the set. I erased that. Did you remember? I drew this blue circle around. It means that it should cover everything, but it has something new. So if 5 is not a complex number, then we are in trouble. So it means that there is a complete distinction between real numbers and that one. Yes?
Get a positive number like that. If you have like negative I squared, it would be this.
No, any number that can be written in this form is called a complex number. But do you think, for example, that is exactly the same spirit, you know? If I ask you, is this a rational number? What is your answer?
Yes.
Rational numbers are fractions, but is this a fraction?
No.
No, but you can write it as a form of fraction by writing it 2/1. You can write 1/2. Yes. So this is the reason that 2 is considered to be a rational number.
So do you mean that basically every number is part of all the categories? Well,
okay, but why? Why 5 is also a complex number? It's of course a real number,
yeah.
but it is also a complex number. So complex number is the biggest system that we have. It covers every number. The reason is that 5, by the rules of the game that we have learned so far, what do you expect to write? We can write it like this. Yes? Because 5 is just 5 plus 0 times I. 0 times I, that's the same rule that we know, and we are supposed to keep those rules. So this is the same thing. But is this a complex number? Yes. If I ask you what is the real part, you say 5. What is the imaginary part? 0. So every real number, because of this equation, every real number like A can be written as A plus 0 times I. And any combination of this form is defined to be a complex number, so it means that any real number is indeed a complex number. So the picture that I drew as a circle containing all of them was actually more or less correct. So this is something that I want you to know. Every real number is also a complex number. Yes? So that picture was correct. This is something that I want you to know. And there is also another terminology, yes?
Doesn't it mean that every number is a complex number?
Yes, every number is a complex number.
Okay.
That's completely correct. But I want you to understand the distinctions as well. Yes, every number, because this is the biggest possible circle, it is clear that it contains everything. Yes? There are some possibilities. So here, if a number 5 is a number, if I ask you what is the real part of 5, it is 5. What is the imaginary part of 5?
0.
0. This is not very strange. There is nothing imaginary about 5, so the imaginary part is 0 actually. And now, there are some numbers whose real parts are 0. For example, for the I, like I itself. By the way, is I imaginary number?
Yes.
Because I can write it plus 0 plus 1 times I. Yes? Then if I ask you what is the real part of I, what is your answer?
0.
0. What is the imaginary part of I itself?
1.
1. Okay? Now if I ask you about 2I. 2I, what is the real part of 2I? 0. What is the imaginary part? 2. The numbers that are complex, but the real part is 0, are called pure imaginary. Okay? So what is a pure imaginary number? A pure imaginary number is a complex number whose real part is equal to 0. Okay? A pure imaginary number is a complex number whose real part is equal to 0. These are the words. These are not something very hard that you say that I don't understand. I'm just defining you these words. Okay. Now that we have a new system of numbers what is coming next, do you think? If you wanted to add something to the systems that you want, if you don't do any algebra with those numbers, more or less they are useless. So we need to know how to add them, for example, how to multiply them, subtract them, raise them to some powers, divide them, or whatever we do with numbers, we want to be also able to do with this one. And Gauss actually mentioned, every rule that you learned so far, I want to keep it. I just added one single equality on top of that, and that is I squared is equal to minus 1. So that is the only thing. So the algebra is very, very simple. Okay. So for example, I just write something. I'm sure that you can immediately answer this, even you don't know how should I define that. For example, I give you a complex number, 5 plus 2i. I give you another complex number, say 6 plus 7i. I ask you to add them. What do you think would be the sum between these two? What is your guess? Yes?
11 plus 9i.
Exactly. That is the natural way. Because I want to keep the rules of the game as before. I'm not going to change anything. 5 plus 6 is just 11, as we learned it before. And 2i plus 7i. I have 2 i's, 7 i's are added to it. Who cares about I? Whatever I is, I have 2 of them, and I have 7 of them. It means that I have 9 of them. Yes?
I have 7 eyes.
Yes. Yes. Actually, I have more, 9 eyes.
You have 9 eyes.
Yes. So this is the sum. Okay? The difference is the same, but let us explore what is the product. Let us explore what is the product. 5 plus 2i. I want to multiply it by 6 plus 7i. What do you think I should start with? How should I start?
Start adding the real numbers.
No, I'm multiplying them, by the way.
Oh, okay.
And by the way,
Start multiplying the real
am I
numbers.
allowed to add 5 to 2?
No,
Why?
because it's imaginary.
No.
Well, okay, they're both.
No, be careful. Why I
Okay.
cannot add? Because I told you every rule I want to keep as before. What is the operation between 2 and I? It's what? 2 and I. Multiplication. And this operation is addition. Which one has the priority? Multiplication. I told you that I want to keep the rules the same. So it means that I am not allowed to add 2 to 5 because first I have to multiply 2 by I. It's this combination is exactly when I write 5 plus 2x. Can I add 5 to 2? No, because the priority is with this product, but I cannot do this product because I don't know x. Yes? What happens if I want to multiply it? What is your suggestion? How should I start? Yes?
Multiply 5 times 6.
And then?
Then 2i times 7 1i.
No, why are you confused?
Correct.
I want to multiply every term by every term. That's it. Yes? So I want to do this. I multiply 5 by 6. I want to keep the rules of the game as before. So it becomes 30. And then 5 times 7i, which becomes 35i. And 2i times 6 becomes plus 12i. And then 2i times 7i becomes 14i squared. Yes? But then, between 35 i's and 12 i's, I see these are similar. So I have 30. I have 35 i's. I add 12 I on top of that. It becomes what? 47 i's. But the only rule of the game that is new is you know something about I squared. Yes?
It's -1.
It's -1, and you have to show me in the exam that you are respecting the rule. Even though if you write it I squared and leave it, that is technically correct, but you have to use I squared equal to -1. So this I squared is equal to -1. -1 times 14 is -14. But no one leaves this like that, because 30 and -14 becomes 16. So the answer becomes 16 plus 47i. So that is the product of these two numbers. So in addition and subtraction, you actually don't need this new rule at all. But what happens is that when I multiply two i's, when multiplication of i's become a problem, then might be I have to use this. Is that clear? Let me ask you some questions about I itself. There are some properties that I want you to understand. And strange things can happen, of course. By strange thing, it doesn't mean that. It means that probably you don't expect them based on the intuition that you have learned from real numbers. So, by the way, what do you think I can say about I to the power of 3? Can I simplify this a little bit more? Yes?
Negative I.
It's negative I. Why? Because I to the power of 3, don't say it is -1 or 1. You have to follow the rules of the game, yes? We don't know. I just know I squared is -1, nothing else. Exactly this rule. So it means that if I want to answer something here, I have to only use this and the rules of the game that I have learned so far. For example, everyone, based on the previous rules, knows that I to the power of 3 can be written as I to the power of 2 multiplied by an additional I. Is that understandable? If you ask me why, because I told you I want to keep the rules the same. Okay, but now I can write -1 for this one. Yes? So it becomes -1 times I. But again, I want to keep the rules the same. The same is that any number multiplied by -1 is negative of that number. So it means that I to the power of 3 is -I. Is that understandable?
Yes.
So what is I to the power of 4?
I squared, -1.
No,
No.
it's 1. Yes, as you said. Because I to the power of 4 is I squared to the power of 2. Agree? Why I have written this? Because this is the rule of the game from my previous learning. But now, today, we just learned one new rule. Instead of I squared, I put -1 here. So it becomes -1 to the power of 2. But -1 to the power of 2 means -1 multiplied by -1, so the answer is 1. So you see that I to the power of 3 is equal to -1. I to the power of 4 is equal to 1. So I to the power of 4 is a real number, even though I itself was an imaginary number. Yes? So what is I to the power of 5? If I give you this to calculate, it is better to calculate it this way. Because if you want to answer this question, you need to make as much as possible. You need to make use of this as much as possible. So instead of I5, I write I to the power of 2, and then another power of 2. So far, it becomes 4th power. Yes, but this is 5th power. So I have to multiply it by an extra I. So what is I squared now? It's -1. So what is -1 to the power of 2, then multiplied by an extra I. -1 to the power of 2 is 1, multiplied by I is positive I. So you see, you can continue this list. I2 was the first in the list, is -1. I to the power of 3, we calculated, it turns out to be -I. I to the 4 becomes 1, and I to the 5 becomes I. And then you can continue this list if you want to. Yes?
Yes.
So for example, can you tell me what is I to the power of 501? You don't need to go step by step. So how should I write I to the power of 501? You need to make use of I squared. So it means that you need to think, how can I write this so that I squared becomes transparent? So how should I write that? So I have to put I squared here. But my exponent is 501. So what can I put here to go close to this? As close as possible. What? For example, if I put 100 here, 100 times 2 becomes 200. So I can increase it still.
250.
250.
Won't be
Exactly.
exact, but it's close.
So it is very close, but there is one more thing that I need. How much I need?
Times I.
1 I. So I need to multiply by I. Yes? So is that it's not hard, by the way. 501 can be written as 2 times 250, which is 500 plus one more. Why this is useful? Because I only know about I squared. But I squared is given to be minus 1, so it becomes minus 1 to the power of 250, and then I want to multiply it by I. But you don't need to suffer to calculate this. Minus 1 to the power 250, what that is? 1, because that's an even power. It means that I am multiplying minus 1 by itself even number of times. So what happens, this part is 1 multiplied by I is just I. So that's it. I to power 501 is just I. Is that clear? So whenever you want to answer something about high powers of I, you have to do it through second power of I. You need to write it in a way that you can answer this. Okay. So for example, let us talk about this. In the real numbers, do you have any suggestion? Do you have any number whose reciprocal is equal to its negative? For example, what is the reciprocal of 2? It's 1 over 2. It is not minus 2. Yes? What is the reciprocal of 3? It's 1 over 3. It is not minus 1 or minus 3. But in imaginary numbers, there is a number whose reciprocal is equal to negative itself. What that number is? The number is I again. But let us explore it. Because I am claiming that there is no difference between this number and its negative. They are the same. So this is a little bit counterintuitive, yes, but these things can happen when you have a new rule. Might be some new possibilities actually emerge. So why these two? Can you motivate me? Why these two numbers are the same? If I want to keep all the rules as before, on top of that, I want to add this new rule. Why do you think 1 over I should be equal to its negative? So do you see, this is inevitable. This is a consequence of the game coming in. So that's the problem. As far as you don't get any inconsistencies, this system mathematically works. Okay, so this is, I cannot avoid that. So in the middle of the game, I cannot say that I don't like this. No, this is a consequence of my assumptions. Why do you think that this is correct? Yes?
Maybe the negative power.
No, why this is correct? Let us do it. So you say that I squared is equal to minus 1. Do you agree? I want to keep the rules of the game the same as before. So instead of I squared, people can write I times I. Yes? And instead of minus 1, I can keep it like that. Then I divide by I. So I divide everything by I. And then one of these i's and one of these i's are cancelled because this is a factor, it's a product. And then I want to keep the rules as before. Then what is happening here, this is I, equals to minus 1 over I. And then I multiply both sides by a negative sign. It becomes minus I is equal to 1 over I. So that's it. So if you like this rule of the game, it's inevitable. You have to like this one as well. If you don't like it, you need to go back and change the rule of the game. So this is a consequence of what you have actually given us. So is that clear now? Okay, but what do you expect? If I give you two numbers, for example, you have an understanding of equality. When I give you 5 and I give you 10 over 2, you can put equality sign between them and you understand them. And now I want to ask you the same thing. When do you think it is good to define two complex numbers to be equal? So it means that they should be somehow identical. So what is the natural way to say, for example, when do you think that this complex number is equal to this complex number? When do you think it is suitable to define equality? How I should define the equality between these two? It's very, very natural. It's so obvious, yes? Exactly. So this is very important to understand. That is the definition. We say that two complex numbers are equal if and only if the real parts are the same and the imaginary parts are the same. So please write it down somewhere. So we say that A plus BI is equal to C plus DI if and only if, this is the definition, that the real part of the left-hand side is equal to the real part of the right-hand side, and this is the symbol for and. The imaginary part of the left-hand side is equal to the imaginary part of the right-hand side. So this is the definition of two complex numbers to be equal. Yes?
Did you mean to write A?
Yeah, thank you very much. Yes, yes. C and then B. Thank you very much. Yeah. So this is why, by the way, this is why complex numbers are so powerful. The reason is, if I give you equality of two numbers, two real numbers, how many pieces of information I am providing for you? If I say that number X is equal to number Y, if I say two real numbers are equal, how many pieces of information I am providing for you?
Two.
Just, why do you say two? I say X is equal to Y. How many pieces of information are there?
Two.
Why?
X. You said Y. I'm thinking that X is equal to Y and Y is equal to X.
This is not two pieces of information.
Okay, it's
This
one
is
piece of information.
The
Yeah.
equality of two numbers, X and Y. Yes? So equality of two real numbers is just one piece of information. But equality of two complex numbers, how many pieces of information are there?
Two.
Two, yes, because
Yes.
equality of real numbers, finally two, yes? And equality of the imaginary parts. So it means that if I ask you to solve this equation, let me write it like this. If I ask you X plus IY, I is the famous imaginary unit, so it means that I know about it. It's a strange creature, but who cares? I know about it. But X and Y are real numbers. Two pieces are missing here. But let me say that I saw this complex number is 5i. Immediately I can answer both of them. I already know X, I already know Y. What are they? What is X if this equality is right? Yes? X is 0, Y is 5. So you see how many equalities I have? One. So it's one piece of information. But how many unknowns I have? Two, X and Y. With one equation, I can solve both of them. So according to definition, it tells me that X, the real part of it, according to definition, should be the real part. There is no real part here, it's 0. And the second one should be equal to 5. So it means that with one piece of info, actually, equalities of complex numbers always contain two pieces of information. One regarding the real part and one regarding the imaginary. Okay. I don't know why they haven't talked about division, but I think we can talk about that as well. But before doing that, let us do some squaring patterns, quadratic patterns, conjugate patterns. We can do all of them with complex numbers. For example, if I give you, this is very strange. This is very nice. Let us calculate this. 1 plus I squared. So how should I do that? Can I use a squaring pattern? The answer is yes, because we agreed on to have all the rules available. On top of that, we want to add one new rule. So if I give you 1 plus x to power 2 in the beginning of Math 2C, we learned how to use the squaring pattern here. So I am saying that we want to keep the rules the same, so I can use the pattern again here. So what happens? It becomes the first one to power 2, which is 1. 2 times the first one times the second one, plus the second one to power 2. But if you stop here, it is not complete, because you need to show that you respect this new rule, that I squared is equal to -1. And I squared appears here. So what should I do? I should write it as 1 plus 2i. Instead of I squared, I can write -1. But -1 suddenly cancels that minus sign, so the answer becomes 2i. So 1 plus I to squared is simpler. You see, if I want to calculate this, I have to write 1 plus 2x plus x squared. This is comparable. The structure here is comparable to structure here, but this is the end of the problem here. This is not the end of the problem here, because now I have a new rule. I add it and I get 2i. Yes, is that clear? So even though we haven't studied power 3, let us use this to calculate this. 1 plus I to power 3. So how should we do that? Tell me, what should I do?
You first do a squaring pattern, and then you times it by it once more.
Once more. So let us write. So it becomes 1 plus I to power 2 times 1 plus I.
Exactly.
Yes? And then this part I have already calculated. It is 2i. So this becomes 2i multiplied by 1 plus I. But this is not the end. You have to continue. So it becomes 2 times I. 2i times I squared becomes, so 2 times I becomes 2i squared. But then this I squared should be replaced by -1 again. So what happens? It becomes 2i negative 2. Usually, if you write it like that, that's completely okay with me. But if you want to respect the rules, it's better. It's not mandatory. It's completely okay if you leave it like that. But if you want, we write the real part first and the imaginary part next. It's okay if you write it like that. So what is the real part? Can you tell me?
-2.
-2, exactly. What is the imaginary part? 2. But of course, I would prefer to write it in that way. Okay, so an exam question could be like this. An exam question could be like this. Find the imaginary and the real part of this number. Okay? If you want to answer the real part and the imaginary part, you have to write your complex number in this standard form. The number next to I is the imaginary part. The number without I is the real part. So if I ask you find the real and imaginary part of this number, you cannot do it directly because this is not still in the standard form. So you have to do some calculations to turn it into the standard form, and then you can immediately answer what is the real part and what is the imaginary. Yes? Yes?
So on an exam, would that question be EC or A level?
I haven't decided yet. I need to. I have to look at the level of exercises.
If
How
I
about-
say it's super, super, super hard, will you make it an
It's
A
so
question?
hard.
It's very difficult.
Yeah, it's
So if it's
totally
very difficult, I
A-level.
probably will not give it to you.
No,
Because the
no,
problem is-
solvable, but
it's just so we can make it.
yes.
Yeah,
Yeah.
it's like A plus, but yeah, we
So
can set it.
I can do something. If there is one person in the class can solve it, and no one else, I can consider it an A. Yes.
One person.
No, not one person, but usually 30% of the people, if they can solve it, that is a good A level. But it is very, very hard to judge, because I have seen many examples are hard for me, but easier for other people, and the other way around. It's hard to judge about these. Forget about. Try to enjoy the new rule of the game. Okay. Okay. So now let us do something else. What do you think about this? It's also a nice pattern. 5 minus 2i, I multiply it by 5 plus 2i. Do you recognize any pattern that you can name it here? Yes, Ruben?
Conjugate.
Conjugate. But there is something interesting happens here. There is something interesting here. 5, what is the answer if I want to use the conjugate pattern? It becomes the first one to the 2. Why this is conjugate pattern? Because I have 2 expressions, once subtracted, the same 2 expressions added, I want to multiply them. So that is the conjugate pattern, yes? So the conjugate pattern tells me, raise the first one to power 2, raise the second one to power 2, but the sign is always negative. So I'm just following the conjugate pattern, yes? But everyone knows about 5 to power 2, hopefully. So it is 25. What can I write for 2i squared? Can you tell me? Yes?
It's 4 because 2 times 2, and it's -1 because I times I.
Okay, but let us not, yeah, that's correct. I would write it minus 4i squared. First of all, this minus sign is here, and this 2 is not affecting this, this remains negative. But now, as Gustav said, this is the new rule of the game, which was absent before, but this is -1. So then it becomes 25 minus 4 times -1. But then this becomes simply 25 plus 4, and it becomes 29. So that's interesting, yes? I multiply 2 complex numbers. It is a real number. Of course, any real number is already a complex number. So if I ask you what is the real part of this combination, this calculation shows it is 29. If I ask you what is the imaginary part of this, you would say it is 0 because there is no I left. So this is also one type of calculation. So do you remember I talked about, if I ask you, I want to remember, there's still a little bit of time. So do you remember if I ask you to factorize this, what is the factorization of this? This should be immediate. What's the answer? Yes, just say it.
X plus y minus x minus y.
Exactly. And then you remember I told you that conjugate that pattern only works if this is negative. But now, if I go to complex numbers, this is also a conjugate pattern.
How?
So this is why I will talk about that. This strange things can happen. I want you to know about them. These are not part of your lessons, even though this is not very hard thing that you cannot understand. So if you remember, if you go back and watch the videos, you see that always I'm emphasizing that if I have the difference of 2 completed squares, that's a conjugate pattern. Because we didn't want to work with a complex numbers. But if I want to work with complex numbers, this is also a conjugate pattern. But how? In this way. X squared plus y squared. Instead of y squared, I can write x minus y squared. Yes? Because minus becomes positive.
Yeah.
But instead of minus is squared, I can write x squared. But then I would write it y to power 2. Why? Let us check. Minus sign, x squared. Now let us look here. I to power 2 becomes -1. Y to power 2 becomes y squared. If I multiply them, it becomes minus y squared. So what I have written is completely correct. But then what happens? The sum of 2 complete squares is now written as the difference between 2 complete squares. But the price that we are paying is that we have to bring I in. And then I can factorize it. I can write it as x minus iy and times x plus iy. So it means that I was able to factorize it, but I was not able to factorize it in the real numbers. So if you remember, I talked about that it depends on which set. I don't know. For example, if I think GeoGebra is like this, if you give this GeoGebra to factorize, the GeoGebra will ask you on which set do you want to do the factorization. If you say, I want to do it on real numbers, it will return you the same answer back. It is not possible to factorize it on the set of real numbers. But if you say that, for example, I want to factorize it on the set of complex numbers, then the same expression becomes factorized in this way. Because the coefficients are not in the set of real numbers, the coefficients are now in the complex numbers. So if you bring this new rule of the game, you need to be very careful. There are very far consequences coming on. So you need to explore them well. But you don't need to be worried about that much. This algebra I expect you to know. I give you complex numbers, I ask you to add them, multiply them, and then raise them to some powers. Division is not discussed in the book, but I will tell you next time about division. Division is also very simple, it's not hard. But then the reason that we come to this is solving equations. Now, can you tell me how can we solve this equation finally? How can I solve this equation? I move 1 to the right, it becomes x squared is equal to minus 1. If the teacher asks you to solve this on the real numbers, you say there are no solutions, finished. Okay? If I want to ask you to solve it on complex numbers, I explicitly mention that. Yes? No, if I want you to solve it in complex numbers, I have to explicitly mention that.
So real numbers are the standard.
The standard ones, yes. Yes?
So is x equal to I?
There's one flaw to that.
Okay.
So let me ask you this question. X equal to 2 is equal to 1. Forget about this and solve this one. What is the answer?
Then it's just square root of 1, which is 1.
No, again, you made the same mistake.
Oh, plus minus.
Plus minus 1. Yes? That's the same story here. So the answer to this I is, of course, one answer, but the other answer is minus I. So it's plus minus I. There are two answers, yes? So because if I ask you to calculate I squared, your answer is minus 1. This is the new rule of the game. If I ask you calculate minus I to power 2, let us see what happens here. Minus I to power 2 means minus I times minus I. But minus times minus is positive. You get I squared again. But what is I squared? I squared is minus 1. So if I ask you, give me a number whose second power is minus 1, there is no 1. There are two numbers. One of them is I, the other one is minus I. So the answer to this equation is plus or minus I. Okay? In order for you not to get confused, you can do something like this. It is not a good way of talking about that. So when you say I squared is minus 1, it means some books define I to be square root of minus 1. This is the same level of strangeness, yes? I squared is equal to 1. If I ask you this in the beginning of Math 2C, you would say it's nonsense because under the square root sign, I have a negative number. But when I'm dealing with complex numbers, this is okay. So my idea is to have this in mind as well. If I want to solve this equation, when I wanted to solve this, I would write x is equal to plus minus a square root of 1, but a square root of 1 is 1, people write plus or minus 1. In the same spirit, if you want to solve this, I would say that, okay, you can do it like this. You can write x is equal to plus or minus a square root of minus 1. But if you leave it like this, it means that you are not respecting the rule of the game. So you need to replace the square root of minus 1 by I. So it becomes plus or minus I. For example, if I ask you to solve this, how do you solve this? You would say that x is equal to plus or minus. You can pretend that everything is okay. So you put the square root of minus 4, but you realize that something is odd there, yes? If you leave it like that, technically it is not wrong. Square root of minus 4, but you need to bring in I. This is what is wanted, expected from you. How can I write this? You know that you can write it as plus or minus a square root of 4 multiplied by square root of minus 1. Yes? Square root of 4 multiplied by square root of 1. But what is a square root of 4? It is 2. What is the square root of minus 1? Is I. So the answer to this is plus 2i or negative 2i. Is that understandable? So I will work on these equations next time. Okay? So then everything would be finalized. No questions? Thank you. Thank you. Thank you very much. Thank you. Bye bye for the people who are here. I didn't check the attendance actually, but
We
It's fine.
usually
Bye-bye.
check attendance.
I shouldn't expose myself to say no.